Okay, 3.1 is on integration by part. Okay, so when I take the derivative of two functions being multiplied together, we use something called the product rule. Okay, that's something that you should have learned last semester. U of x times v prime of x plus v of x times u prime of x. Okay. Okay, when we integrate a product of two functions, we have to do it in kind of a roundabout way. We have to say, well, if we integrate the derivative of this thing, of u and v, u times v, this is really equal to, okay, the integral of u dv, okay, this thing here, u dv plus the integral of v du. Okay, the integral of u times the derivative of v plus the integral of v times the derivative of u. That comes to us from the product rule. Okay, this gives us, okay, all I'm doing is integrating each piece of what's above, of the line above. Okay, this gives us uv is equal to the integral of u dv plus the integral of v du. Okay, subtracting v du from both sides, we obtain uv minus the integral v du is equal to the integral of u dv. Okay. And so how does this help us? You know, it looks like things got a little bit more complicated. They actually got a little bit easier to integrate. Let me explain. So if I take u dv and I say, well, that's uv minus the integral of v du, then say that u is f of x and dv is g of x. Then all I have to do is integrate g of x to figure out what v is, and I'll be able and find the derivative of f of x, and we can plug it into this formula. Okay, the integral of f of x g of x is going to be equal to u, which is f of x, times the integral of g of x dx minus the integral of v, which is the integral of gx dx, okay, times du, which is the derivative of f of x. I'll just call that f prime of x dx. Okay. Okay, so we're going to let one function be u, and we're going to let one function be dv. Okay, when we integrate by parts. Okay, this is integration by parts. Let one function be u, and the other function be dv. Okay, when we integrate two functions, the product of two functions. We did a little bit of calculus manipulation. Let's see how this works in practice. Okay. Number one, find the integral of x sine x dx. Okay, so we want to know what's going to be u and what's going to be dv, so that we can use our newfound formula. Okay, the integral of u dv is equal to uv minus the integral of v du. Okay, so we have an x as one of our functions, and we have a sine x as another one of our functions. Okay, so we need to know what's going to be the best one to take the derivative of when I get my du, and what's going to be the best to take the integral of in order to get my v. Right? So, or take the antiderivative of in order to get v. Okay, you can think of it either way. Okay, so we use this kind of mnemonic device to figure out, well, what should we use for u? And we use a mnemonic device called LIATE. Okay, L-I-A-T-E. And this is kind of the order of preference for u. Okay, it's the order of priority for what u should be. And so the L stands for logarithmic. The I stands for inverse trigonometric. Oops. The A stands for algebraic. The T stands for trigonometric. And the E stands for exponential. And again, this is the order of priority that we want to take for u. Okay, and so we just remember LIATE, and it's okay, logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential. Okay, so that's how I want to take it. So which one's going to come first here? Okay, is it going to be algebraic for the x or trigonometric for the sine?
Algebraic.
Algebraic.
Yeah, algebraic for the x. Thank you. Thank you, Brenda. I see that as well. Okay, so it's going to be algebraic for the x. So let's let u equal x, and let's let dv equal sine x dx. Right? So what happens when I take the derivative of u? I get just 1 dx. 1 times dx, or just dx. What happens when I take the integral of sine? What is the integral of sine?
Negative cosine x.
Thank you, Va. It is negative cosine x. So now we're going to do kind of a crisscross applesauce type of thing, where I'm going to pair up uv and then v du. So I kind of say I'm going to go here, and then I'm going to go there. uv v du. I always kind of just draw these arrows to remind me of the order. Okay. So let u equals x, v equal negative cosine x, du is dx, and dv is equal to sine x dx. So crisscross applesauce, we have ux, u and v, right? Remember, because it's uv minus the integral of v du. So I'm going to multiply u times v. That's going to give me negative x times cosine x minus the integral of v du. That's negative cosine x dx. So I can pull out that negative if I want. And that's going to give me negative x cosine x plus the integral of cosine. Now, what's the integral of cosine?
Sine x.
Sine, yeah, the integral is a positive sign, so that's sine x plus c. And that gives me the integral of x sine x dx. It's kind of a nice result there. And that is integration by parts. Okay, so let's do a few more of these. Okay, number 2. Evaluate the integral of the natural log of x dx. Okay, so what's u going to be? And what's dv going to be? Well, they don't really have two functions. But I can create another one. Okay? We know what the derivative of natural log is. Now we're trying to find out what the integral of natural log is using integration by parts. Remember, what's the derivative of a natural log? If I let u be natural log or logarithmic, which I really should because of why? Why should I let u be the natural log?
Liot.
Liate, right? Yeah, exactly. Liate. And what comes first for the L? The L is
Logarithmic.
Yes, thank you very much. So now what is interesting here is we have the ability to turn an integral of natural log into a derivative of natural log, which is very, very helpful because it turns something that's logarithmic into something algebraic. Because what is the derivative of natural log?
1 over x.
1 over x dx. Okay, yeah, thank you very much. It's 1 over x dx. So what should my dv be?
A 1.
It could be 1 dx, right? And what's the integral of just 1?
X.
X, yeah, thank you, Ishan. It is x. So now I have my uv v du. So we're going to say that uv minus the integral v du is going to be x natural log x, right? X natural log of x minus the integral of v, which is x, times the du, which is 1 over x dx. And notice that the x and the 1 over x will cancel out. And so I'm just left with x natural log of x minus the integral of dx. Well, we just saw what that integral was. What was the integral of dx? Yeah, it was x, right? So now what can we do? We can factor out an x times the natural log of x minus 1. That will be what my result is. So I get x times the quantity natural log x minus 1. And now we have the ability to integrate natural logs. Okay, we didn't have that ability before. We could only differentiate them. We could only differentiate natural logs, but now we have the power to integrate natural logs, which is very nice. Oh, don't forget my plus c. Always plus c. Okay, always plus. Okay, is this making sense? So far, so good?
Yeah, so far so good.
Okay, let's jump into number 3 here. Let's turn up things a little bit. Okay, we can do successive integration by parts to cut something down that is more complicated into something less and less complicated. So we can do this integration by parts in iterations if we need to. So let's find the integral of t squared e to the t dt. U equals t squared, right? Oh, sorry, I'm kind of giving it away. What should we use for u? Remember, LIH, right? So notice that we have an algebraic and we have an exponential, right? So which one should be u?
T squared?
Yeah, the algebraic, t squared, exactly. And the dv, e to the t dt. Make sure you put that dt there. It goes along with it. Okay, what's the integral of e to the t?
E to the t.
Itself, exactly. And the derivative of 2t, I'm sorry, I gave it away again, sorry. The integral of, or the derivative of t squared is 2t dt. So let's do our crisscross, okay? And uv is going to be t squared e to the t minus the integral of v du, which is 2 e to the t dt. And you're like, well, that didn't really get me anything. You know, we still have an integral with regard to, sorry, this is a 2t. We still have an integral that involves a t and an e to the t. So it didn't really help us much, but it did because we're down 1 power. We dropped 1 power, and the next time we drop a power, we're going to go to a constant, and that's going to help us out a lot. So what we're going to do is we're going to do integration by parts again. So do integration by parts again. Okay. And so in this case, again, the u is going to be the 2t. The dv is going to be the e to the t dt. The derivative of u is going to be equal to 2 dt. And the integral of v, the integral of dv is going to be e to the t. And once again, I'm going to go crisscross. Okay. And so this time we're going to make sure that we put things in parentheses because we don't want to mess up on our negative signs and our you know, we might end up with sign errors if we don't group things properly. So this is t squared e to the t minus, okay, uv, that's 2t e to the t, okay, minus the integral of v du, which is 2e to the t dt. And again, I'm going to put that in parentheses so I don't mess up on any signs, because I am going to have to distribute those signs in a second. So this is going to give me t squared e to the t minus 2t e to the t minus the integral of 2e to the t is just itself. It's 2e to the t. Okay, and then this is plus c since I'm done integrating. I'm going to put a plus c there. Okay. So now I'm just going to distribute and factor. So I get t squared e to the t minus 2t e to the t plus 2 e to the t plus c. I'm going to factor out an e to the t. I get t squared minus 2t plus 2 plus c. Okay. And what was that? That was equal to, again, t squared e to the t dt. So we had to end up doing integration by parts twice, but we were able to cut that algebraic polynomial down from t squared down to t and then down to 2. Let's try another one. Okay, number 4. Evaluate the integral e to the x sine x dx, right? So this one's an interesting one. Again, let's use Liate. Okay, we're integrating 2 functions being multiplied, so we have to use integration by parts. So what am I going to choose for my u?
E to the x.
But e to the x is exponential, right?
Oh,
What comes
Yeah.
before that?
trigonometric.
Yeah, trigonometric, right? Trig. Okay, don't get that confused with inverse trig, which comes before that. Okay, but so we're going to have to use trig on this one. Sine x, and then dv is equal to e to the x dx. So what is du? What's the derivative of sine x?
Cos x?
Yep, cosine x dx. And the integral of e to the x, we saw that was just e to the x. Okay, so let's go sine x e to the x, and then e to the x cosine x. So uv minus the integral v du. Okay, so u go and v, that's e to the x sine x minus the integral of e to the x cosine x dx. Okay, and you might be puzzled because you're like, well, if we do this again, aren't we just gonna keep getting e to the x's and either cosine x's and sines? And we will. And we're gonna use that fact in the next step to help us actually solve for this integral. This thing is gonna oscillate back and forth between sine and cosine and sine and cosine, and it's just gonna keep oscillating over and over again. So you would think that this would go on infinitely if we just kept integrating by parts, but we can actually use the fact that it oscillates to our advantage. Okay. So we're going to do this one more time. So u is equal to cosine x, and then dv is equal to e to the x dx. V would be equal to e to the x, and now du is equal to negative sine x dx. Crisscross. Okay, so we've got uv, which is e to the x cosine x. Make sure that you know that this is inside of parentheses because we already have e to the x sine x on the outside. Okay, that's inside of parentheses. Okay, and then this is minus the integral, minus the integral of negative e to the x sine x dx. And now I want to say, well, what does this equal to? This equals, okay, I'm going to distribute the negatives in a minute and try to reconcile the negatives. But what does this equal? This equals e to the x sine x dx. Okay, so let's distribute the negative and reconcile. We've got one negative for e to the x cosine x. And we've got three negatives for e to the x sine x, the integral. So that's going to be a negative result because I know three negatives make a negative. Okay, and so now we have the exact same thing on the right-hand side of the equation as we do the left-hand side. So what do you think we're going to do?
Subtract them and cancel them.
Close, close. We're actually going to add them. Okay, because what that's going to allow me to do is it's going to allow me to get everything that's involved with a integral on the left-hand side and everything that is not being integrated on the right-hand side. So let's add e to the x sine x dx to both sides. So this becomes 2 e to the x sine x dx. This equals e to the x sine x minus e to the x cosine x. I'm going to put a plus c there because everything on the right-hand side has now been integrated. I'm going to divide through by 2. Okay, and then I'm going to factor out the e to the x. So the integral of e to the x sine x dx is equal to 1/2 e to the x times the sine x minus cosine x plus c. It's pretty slick the way that works. Okay. Okay, if we have limits of integration, we can still do integration by parts. A to b of u dv is equal to uv evaluated from a to b minus the integral a to b of v du. We just use that. Okay. So let's do one with limits of integration. Okay. Okay, we want the integral from 0 to 1 of inverse tangent of x dx. Okay. Inverse tangent of x dx. So the derivative of inverse tangent, I understand. The derivative of inverse tangent just like with the derivative of natural log, I understood what derivative of natural log was. The derivative of inverse tangent is equal to 1 over 1 plus x squared. Okay, and so we can use here again that trick about integration by parts that turns the integration into a derivative, which is nice because the derivative here is a whole lot nicer than you know, dealing with the derivative is a whole lot nicer than trying to integrate an inverse tangent function. So let's let's try to do that. So U and dv, what should be my U? Using Lyate, this is an inverse trig function. Right? What comes first, inverse trig or algebraic?
Inverse trig.
Inverse trig, right? Inverse trig comes first, so we're going to turn this integration into a derivation. And so we're going to say that that's 1 over 1 plus x squared dx. It turns in something that is inverse trigonometric, it turns something that's trigonometric into something that is now algebraic, which is really nice. Okay, when I differentiate, I get something that is very complicated inverse trigonometric function, and then it turns it into a nice algebraic function. Okay, I'm gonna actually move these over because they're kind of bunching up. There we go. About it. Okay, so what is dv then? What's dv going to be equal to?
1 dx.
Yeah, 1 dx. We can put the 1 in there if you want. Okay, 1 dx. What is 1 in terms of Lyate? What type of
Algebraic.
function is 1?
Algebraic.
It's algebraic, exactly. It is algebraic. Okay. So inverse trig comes before algebraic. So we're going to go v is equal to x. Okay, nice. So now we're going to go uv, v to u. Okay, u to v, v to u. This is going to be x times the inverse tangent of x, evaluated from 0 to 1. Okay, minus the integral from 0 to 1 of x over 1 plus x squared dx. Right? Okay, I'm going to do a u sub on this one. This becomes a nice u sub right here. U is equal to 1 plus x squared. Du is equal to 2x dx. I don't have a 2, so I'm going to divide by 2. But I do have the x dx now. Right? So I have this guy, which is this guy. Okay, so let me translate my limits of integration. U of 0 is equal to 1 plus 0 squared, which is 1. U of 1 is equal to 1 plus 1 squared, which is 2. Oh. Okay, and so my new integration will be x inverse tangent of x from 0 to 1 minus the integral from 1 to 2 of 1 over u du over 2. Okay. I could pull out that 1/2. So this is minus 1/2 times the integral of 1 over u. What is the integral of 1 over u?
ln u.
Yeah, natural log, ln u, thank you. Ln u from 1 to 2. Well, this is going to be x inverse tangent of x from 0 to 1 minus 1/2 times the natural log of 1 to 2. Okay, nice, great. Okay, now let's plug in these limits of integration. I'm going to go, okay, 1 times the inverse tangent of 1 minus 0 times the inverse tangent of 0. That's that first one. Minus 1/2 times the natural log of 2 minus 1/2 times the natural log of 1. Okay, that's my second piece. Okay, so a couple things go to 0 here. What's 0 times the inverse tangent of 0?
0,
0. What's the natural log of 1?
0,
Okay, so what's the inverse tangent of 1? Did I stump everybody? What is the inverse tangent of 1?
Pi over 4.
Pi over 4, very good. It is pi over 4. It's my 45-degree angle. So that is pi over 4 minus the natural log of, or 1/2 times the natural log of 2. And so this becomes pi over 4 minus the natural log of 2 to the 1/2 power. And so this becomes pi over 4 minus the natural log of the square root of 2. It's kind of a really cool, it's kind of a really cool result when you think about it. Okay, I mean, what was the original function that we were dealing with? We were dealing with the inverse, the area under the curve for the inverse trigonometric function, inverse tangent of x from 0 to 1. And what did we end up with? We ended up with an answer in terms of pi and a natural log, which is, you know, I mean, you're taking an inverse trig, which is a complicated function, and your answers in terms of pi, which is a irrational number, okay, and one of the most famous irrational numbers, and then you also have natural log of the square root of 2. So we have a square root, which is irrational, natural log, which is, you know, another complicated function. So that's some powerful math here, right? And again, what are we doing? We're really, okay, from 0 to 1 of this inverse tangent function, right? We're finding the area under that curve. Okay, as this thing goes to pi over 2.
Hey, Professor, during the test, if we add something similar to this, will we add plus C to the end of this one too?
No, you won't add plus C. Why?
it's a,
Inverse trig?
Because we had
Function?
bounds.
Because of the limits.
Yeah, the limits, right?
Because of the limits of integration, we can actually get the actual result.
Got it.
Okay. Okay, number 6. Okay, show the reduction formula is valid. We're going to find a power reducing formula for sine. Integral of sine to the nth power of x dx is equal to -1 over n cosine x times the sine of n to the n minus 1th power of x plus n minus 1 over n times the integral of the sine of n minus 2, sine of x to the n minus 2 power dx. So this is called the power reducing formula for integration of sine, of powers of sines. Okay, it's a reduction formula for the powers integration of powers of the sine function. Okay, so let's show that we can do this using integration by parts. Okay, so we're going to take the integral of sine to the n of nth power, sine of x to the nth power dx. Okay, and what I'm going to do is I'm going to break off a sign. Okay, I'm gonna break this up into the integral of sine to the n minus 1 of x times sine x dx. And that's the trick here, is to use integration by parts and then just break it up into two sine functions. Okay, so u is going to be equal to the more complicated sine function. Okay, and I'm going to get sine to the n minus 1th power of x. When I take the derivative of this, I'm going to bring the n minus 1 in front. This becomes sine to the n minus 2 of x. Okay, times, this is a chain rule, right? Times the cosine of x, that's the derivative of sine, dx. Okay, dv is going to be that sine x that I broke off. That means v is negative cosine x. Okay, now I'm going to do my integration by parts. Okay, so this is equal to negative cosine x times sine to the n minus 1th power of x minus the integral of negative cosine x times n minus 1 times the sine of n minus 2 x times cosine x dx. So let's clean that up. This equals negative cosine x times the sine of n minus 1x. I'm going to pull this negative sign out front, and so that becomes a plus. I'm going to multiply the cosine times the cosine, and that's going to become cosine squared. So this is n minus 1 times the sine of n minus 2 times cosine squared x dx. One thing that I'm going to do here, since I have a cosine squared, I'd like to have everything in terms of sine, okay, and not in the integral. So this I'm going to make as 1 minus sine squared x. Okay. So this is going to become negative cosine x sine n minus 1x plus the integral, okay, of n minus 1 times the sine of x to the n minus 1 of x, sine of x to the n minus 1 power, times 1 minus sine squared x dx. Okay. So this is going to be equal to negative cosine x sine to the n minus 1 x plus, I'm going to now distribute. This is the integral of n minus 1 times the sine of n minus 1, sine of x to the n minus 1 power, minus n minus 1 times the sine. Now I got to get the power right here. This is going to go n n minus, oops, did I mess up? Oh, I'm sorry, this should be n minus 2. I don't know why I keep putting n minus 1. This is n minus 2. My bad. Okay, that was back there. That was an n minus 2. Okay, so this, when I distribute the n minus 2 over the 2, those are going to add, and that's just going to become n to the power of n. And then we have our dx. Okay. Okay, so let's break this up into two separate integrals. So this is equal to negative cosine x sine to the n minus 1 x plus the integral of n minus 1 times sine to the n minus 2 of x minus the integral of n minus 1 to the sine of nx dx. And this is equal to the integral of sine to the nx dx. And we're going to use that trick where we're going to take this guy and we're going to add it to both sides. So let's go ahead and add that to both sides. N minus 1 times the sine of nx dx, since we get the same power of sine on both sides. Plus, I'm going to pull that n minus 1 on the outside. Okay, so this is n minus 1 times the integral of sine nx dx. That goes away. And this just becomes 1 on the outside. So if I add these together, I'll get n minus 1 plus 1, which is just n. It's n integrals of sine to the nx dx is equal to, and I swear this is going to get nicer in a second, cosine x sine to the n minus 1x plus the integral, I'm going to pull this n minus 1 outside, n minus 1 times the integral of sine to the n minus 2 x dx. There should be a dx here. And now all I have to do is divide by n. And we end up with what we were looking for. The sine of nx dx is equal to negative 1 over n cosine x sine to the n minus 1 x plus n minus 1 to the integral, or n minus 1 over n, to the integral of sine n minus 2 x dx. And that's our power reducing formula. Now, how would we use this power reducing formula? Well, let's say that we have the integral of sine squared x dx. Okay, n in this case is 2. And so if I plug this now into this formula, this becomes negative 1/2 times cosine x to the times sine to the first power, sine to the 2 minus 1 power, plus 2 minus 1 over 2 times the integral of sine to the 2 minus 2 x dx. Okay, so this is going to be equal to negative 1/2 cosine x. This 2 minus 1 goes to 1, so that's just sine x, plus this is 2 minus 1 over 2, 1/2. And then this is going to be sine to the 2 minus 2, but that's 0. So, and anything to the 0 power is 1. So this just becomes the integral of 1 dx. And so this is equal to negative 1/2 cosine, I'm missing x there. cosine x sine x plus 1/2 times the integral of 1, but that's just x. Okay, plus c. And so I could factor out, well, I can't factor out anything. I can factor out the 1/2. And this becomes x minus cosine x sine x plus c. And that is the integral of sine squared x dx. Okay? And that is section 3.1.